Good morning. My name is John Vandelent. I serve as co-director of the Center for Risk-Based Community Resilience Planning, along with my co-director, Bruce Ellingwood. On behalf of the more than 100 researchers, staff, and collaborators working to understand and model community resilience within the center, welcome to Community Resilience, Modeling, Field Studies, and Implementation. Before we begin the technical portion of the webinar, I'd like to introduce Dr. Howard Harari, Director of the NIST Engineering Laboratory.
Thanks, John. Good morning, everybody, here and on the web. It's a pleasure to be back here in Fort Collins to hear about the progress in the COE's work. And from what I understand, there's been a lot. As many of you know, the Engineering Laboratory at NIST has 4 primary goal areas to define our research portfolio: building, energy, and indoor environment, manufacturing, smart grid and cyber-physical systems, and disaster resilience. We remain very enthusiastic about our partnership with the Community Resilience COE because it aligns so well with our disaster resilience goal, and that's no accident. NIST funded the Community Resilience COE to complement NIST's resilience programs, foster an expanded expertise in resilience through educating scientists and engineers, train future researchers who may someday work with or at NIST, and expand opportunities for NIST to learn from and engage with academia and other stakeholders and customers. On behalf of NIST, I want to say how excited we are to hear about the progress that the COE has made during the past 6 months since we were last together, and a review of the overall progress in the 2 years since the center was initiated, as well as the exciting work starting in year 3 of the center. I'm particularly happy to say that you will hear presentations over the next 2 days from NIST staff who are going to share their research as it aligns with and benefits from the outstanding work of the COE. I'm also encouraged by the staff exchanges that have occurred in recent months, including visits to NIST by key COE personnel and visits by NIST staff to our COE university centers. A recent highlight of our partnership was the deployment of a fully integrated research team to Lumberton, North Carolina, to study the effects of flooding from Hurricane Matthew. The deployment emphasized a study of the effects of Matthew on the local school system. I believe that the Lumberton study will mark a turning point for the way we do disaster studies. The integration by design of field teams made the process truly interdisciplinary from the very beginning. The use of cutting-edge sampling and geospatial recording throughout the study was highly innovative, and the use of longitudinal methods for recovery analysis of building failures should represent a new paradigm for studying the performance of the built environment. I'm particularly looking forward to hearing some of the preliminary findings from this deployment. So that's all from me. I'll let you get on with it. I'm anticipating a great 2 days. John.
Thank you, Howard. For the remainder of the webinar, which is scheduled to last about 2 hours, I'll provide a short overview first. This will be followed by a series of technical topics summarized in a special issue of Sustainable and Resilient Infrastructure, edited by Paolo Gardoni, with each author presenting the theory behind their contribution. This will immediately be followed by a live demonstration of the computational modeling environment known as INCORE under development, and then a few minutes for questions and answers. So for questions and answers, let me jump back one slide. Please email those directly to Professor Hussam Mahmood, and that's hussam.mahmoud@colostate.edu. And we'll get to as many of those as we can in the short time we have, and then try and follow up by email. So then Dr. Terry McAllister from NIST will join me to introduce our first Hindcast in the pursuit of validation of INCORE, the 2011 Joplin, Missouri tornado. Judy Matrani-Reiser, NIST Disaster and Failure Study Programs Lead, will be joined by the Center's Social Science Lead, Walt Peacock, to explain a new approach to field studies with a focus on understanding and modeling community resilience. Hurricane Matthew itself was short-lived along the eastern seaboard, but the devastating flooding that resulted inland lasted for days. The focus of that study was Lumberton, North Carolina, as you heard about from Howard, which is beginning their path to full recovery. We'll close with some additional time for Q&A coordinated by, again, Professor Hussam Mahmood, a researcher within the center. The team has grown slightly since the introductory webinar a year ago. Several center postdocs and students have joined as tenured faculty around the U.S. The team consists of approximately 27 academic faculty, 11 NIST collaborators, and a large number of postdocs and students across numerous institutions. The center's external assessment panel provides the center researchers and NIST with written and verbal reporting related to the center's progress toward its year-end and its long-term goals. The EAP consists of a number of prominent individuals representing engineering, social science, economics, and public policy. The mission of the Center of Excellence is to support measurement science to enable researchers the ability to study and understand the underlying attributes and factors that make communities resilient to hazards. Ultimately, providing risk-informed decision support to community leadership and their constituencies to optimize a combination of public and private investment in resilience planning over time. The Center of Excellence activities focus on three key thrusts, namely Thrust 1, the development of the multi-disciplinary computational environment known as INCOR. To accomplish this requires the collaboration of numerous disciplines and specialists, including structural and geotechnical engineering, coastal engineering, transportation engineering, risk analysis and operations research, economics, software architecture and database management, social sciences and post-disaster investigation and assessment, and interdependency and network analysis. Thrust 2 focuses on standardizing data ontologies, robust data architecture, and developing tools to support the computational environment. Thrust 3, the validation of the data collection process, including its integration into INCOR, through Hindcasts and field studies. And so you may recall the webinar last year focused on Thrust 1. This year, we place equal focus on Thrust 1 and 3 with some information on Thrust 2. So there's a number of center research issues, and to highlight a few, the quantitative tools and metrics for assessing community resilience are in a rudimentary state or even not available. And so this is one current research issue that the center focuses on. Multiple hazards, these are interconnected, interdependent systems, have to be considered. The consideration of uncertainty, both aleatory and epistemic, has to be included to make a fully risk-informed decision or support that decision. And then plans and guidance are needed, and that's perhaps at the year 5 point. And then existing and building and infrastructure systems, as well as new construction, both must be considered. And perhaps one of the most important is that code standards and regulatory documents must contain consistent performance goals, and currently do not. So some of the research and implementation questions that eventually will be answered, or we seek to answer as a team. How can community leaders know how resilient their community is? How can they know if their decisions and investments to improve resilience are making a significant difference? And then how do they deal with the uncertainty and risk? How do they propagate that through the models, and how do they account for that in their decision-making process? So within Thrust 1, the development of INCOR, the team considers individual hazards, including hurricanes, tornadoes, earthquakes, and tsunamis, wildland and urban interface fires, and floods and storm surge. Hurricanes are treated as a multi-hazard problem with wind surge and waves all combined, and modeling coastal inundation, for example, modeling coastal inundation with a research-grade AdCirc mesh for use as input to INCOR. Physical infrastructure consists of building models developed based on principles of engineering and physics, fragilities for damage, loss, functionality, and restoration and recovery. Transportation networks are modeled with the ability to damage bridges, portions of roadways, and soon railway systems. Water systems and electrical power are modeled at the distribution level and can be coupled for dependency, as you'll hear about in the next portion of the webinar. Communication networks have been started and will be expanded upon over this year. Even during the proposal development stages, the team recognized that while physical infrastructure is critical for resilience, the metrics by which a community measures its resilience and recovery are rooted in social science and economics. Thus, there's a team of social scientists working to working on defining performance improvements in community resilience based on adoption and implementation of policies, codes, and standards. Key to this development of optimization strategies for enhancing this includes intelligent algorithms. In order to synthesize the interdisciplinary work being conducted within the Center of Excellence, 4 test beds are currently in progress. Centerville, which you'll hear about in quite a bit of detail shortly, the Seaside, Oregon test bed, the Memphis, Tennessee Metropolitan Statistical Area test bed, and the 4th and newest test bed is Galveston, Texas, including the Boulevard Peninsula, which enables the center researchers to study multiple hazards generated by a hurricane. Each of these test beds incorporates detailed social and economic network modeling to study mitigation strategies, recovery models over time following an event, and optimization in time and space for risk-informed decision support. Key to measuring community resilience is defining resilience metrics in terms of physical, social, and economic systems. General recovery is supported by recovery of physical systems such as time to functionality, but often measured in terms of social and economic factors or metrics. These are metrics such as retaining businesses and related employment, jobs, revenue, resources, change in income distribution, and percentage in poverty, but also considering the most basic and fundamental needs in life, such as survival and safety, food and water, and health. Developing a robust data architecture that allows data to be easily ingested into INCORE or data to be accessed across multiple discipline-specific databases is the focus of Thrust 2. This included NCSA identifying user requirements based on different data set types. For example, fragilities that are a function of more than one intensity measure. To be able to assign these requires building a taxonomy for all hazards, which you'll hear about more in the Joplin Hindcast presentation later in this webcast. Incorporating key data types from economics and social science and the associated metadata, as well as management tools, is a necessity. Key to the development of the robust data architecture is the team's understanding that while we may develop new data types and tools, it's critical to include existing data and ontologies for full synthesis. Thrust 3 consists of validating the full architecture for INCORE, which is made up of tasks 1 and 2. This will be accomplished through a robust series of checks and hindcasts ranging from the single building or infrastructure component level, economic component, to single infrastructure sector validation. This will be done at points in time to validate damage modeling, loss estimation, and functionality and recovery models. The first such hindcast model, as I mentioned, is the 2011 Joplin tornado, which will be introduced by Dr. Terry McAllister shortly. As an example, consider the simplest wind field model for a tornado, shown in the bottom right of this slide. It is based on almost 40 years of tornado data and allows the analyst to model a tornado either with mean values or stochastically with multiple realizations in a community. For the tornado model, one question we seek to answer is, does such a model provide the necessary information for accurate community modeling to support risk-informed decision-making for planners and stakeholders? Validation at each step along the way allows the team to assess and compartmentalize or isolate modeling errors. So as the center matures, each year brings with it a new theme, allowing focus for researchers, students, and NIST collaborators. In year 1, the focus was on team building with a kickoff meeting held almost immediately. The virtual community known as Centerville provided a test bed upon which to focus and begin to develop common terminology across disciplines, or at the very least, understand terminology from other disciplines. The beauty of a virtual community was that it allowed the teams to immediately focus on fundamental developments rather than data collection immediately. Task work plans were fleshed out with key deliverables from each task team carefully articulated, allowing them to be updated every 6 months to this point. Modeling of hazards, particularly hazards other than earthquake, which is relatively mature, was a key theme in year 1 and provided basic loading mechanisms to begin studying community resilience within INCORE. This included tornado, tsunami, and wildland urban interface fires. In year 2, the center team expanded the continued work on dependencies between physical infrastructure and social science, but more prudently began to focus on basic models of interdependency. This was done by expanding the testbed portfolio from a virtual community to add 3 real communities, and those are the 3 introduced earlier. As we begin year 3 of the Center of Excellence, the team's focus is turning to modeling of functionality and recovery modeling at the community level. Key to modeling recovery are accurate but efficient models for interdependency within and across physical, social, and economic infrastructure sectors. In year 4, it's anticipated that in-core architecture will have been modified during year 3 to include temporal aspects of recovery and investment strategies, thereby enabling the team to study risk-informed decision-making strategies. This will include full model applications of in-core version 2.0. In year 5, refinement of in-core and archival documentation of the measurement science developed will continue, but attention will be placed on technical outreach with user workshops. At this stage, most users will be researchers studying community resilience, but likely in collaboration with communities around the US and world. So thank you, and now I would like to welcome Professor Paulo Gardoni, Associate Director of the Center and Editor of Sustainable and Resilient Infrastructure, to the podium to chair the next portion of the webinar. Paulo.
Thank you, John. Well, thank you, Professor van der Leen. In this portion of the webinar, we will talk about a special issue published in the journal Sustainable and Resilient Infrastructure dedicated to the Centerville testbed. Several testbeds have been initiated since the beginning of the center. The testbeds have been designed to, 1, allow center research teams to initiate, test, and modify essential community resilient assessment models and algorithms before the in-core platform becomes fully operational. 2, stress these assessment models in a controlled manner. 3, examine varying degrees of dependency between physical, social, and economic infrastructure systems. And 4, facilitate the interdisciplinary collaborations and approaches to community resilience assessment that will be essential for a center to achieve its ultimate goal. A special issue of the journal Sustainable and Resilient Infrastructure, Volume 1, 2016, Issue 3-4, has been devoted to the first of these testbeds, namely the Centerville virtual community. Sustainable and Resilient Infrastructure is an interdisciplinary journal published by Taylor and Francis that focuses specifically on the sustainable development of resilient communities. The special issue includes the following contributions, and I would like to invite one of the authors of each of these papers to give a short overview on their work. To start, I would like to invite Professor Ellingwood to say a few words about his contribution in the special issue.
Thank you, Paulo. The community resilience depends on the performance of the built environment and in supporting social, economic, and public institutions which individually and collectively are essential for immediate response and for long-term community recovery following an extreme hazard event. Traditional engineering design approaches focus on performance of individual facilities under individual hazards through codes of practice primarily. The aftermath of recent extreme events has revealed the shortcomings of these traditional approaches. Communities are complex entities. They're exposed to numerous natural hazards. Their physical infrastructure systems must function together for community well-being. Construction practices, economic and social support systems, and value systems actually differ greatly from community to community. Accordingly, the advancement and implementation of best practices to enhance community resilience require an integrated approach that involves many different disciplines, including engineering, the social and economic sciences, and the information sciences. The Centerville testbed was introduced early during the first year of the center's research program, and it had really two fundamental purposes. First of all, as Paula mentioned, to enable fundamental resilience assessment algorithms and databases to be developed in a preliminary form, coded and tested at an early stage before the more refined measurement methods and databases for physical, social, and economic systems had been fully developed and matured. And second, and equally important, it was devised to provide a structure for interdisciplinary teams to work together toward a common purpose from the beginning of the center, which is something that's been very, very difficult to achieve in past centers involving interdisciplinary research. The Centerville community is a typical middle-class community situated in the central part of the United States, and you'll learn a great deal more about it in the course of these presentations. I'll just give you a brief overview. The household income average is close to the national average. There are pockets of low to moderate income residents and vulnerable populations within the community. The economy is reasonably well diversified between the business, commercial, economic, and industrial, education, healthcare, and governmental sectors. The population of Centerville is approximately 50,000 people. There are approximately 20,000 households within the community. Of those, 20% are headed by somebody with a college degree. 20% are headed by somebody with less than a high school education. The median household income of about $52,000 is close to the national median. In terms of employment, approximately 32,000 residents in Centerville are employed. The majority are in the retail, services, government, and healthcare areas. In terms of building construction, the built environment of Centerville is modeled with four basic physical infrastructure systems and components: buildings, transportation, water, and electrical power. And we selected these four systems for two reasons. First of all, the fragility models were relatively mature at the time that we started doing the study, at least for the individual systems. And second, they represent distinct topologies. And third, the interdependencies between the water and the electrical power systems in particular could be examined in some detail at a very early stage in the center's research. This is a schematic of the transportation network within the system, within the city. The road network consists of highways, both primary, secondary, community roads. There are four bridges which separate the population centers, which are east of the river, from the major employers and the regional hospitals, on the regional hospital on the west side of the river. So this, having a virtual community like this, allows us to move the various components of the community around to determine what the impact of various configurations might be on its ability to withstand and recover from a disaster. The Centerville water network and the electrical power network both follow the public right-of-way of the road network, and this is very common in urban areas. The electrical power network is modeled at the generation, transmission, and distribution level, but it's not modeled at the individual building supply level. Centerville is susceptible to two primary natural hazards: earthquake and tornado. Last year, we talked briefly about the tornado modeling. This year's presentations that you're going to hear in the following presentations focus more on the earthquake hazard. We imagined a magnitude, a 7-point earthquake with an epicenter of approximately 40 kilometers from the centroid of Centerville, in order to look at the impact of such a scenario event on the distributed infrastructure within the community itself. And so our presentations this morning will focus on losses due to that particular event. The social and economic metrics that we're considering as part of the study are five. I'll give a plug for the NIST-sponsored Center for Resilience, the Community Resilience Panel, which has tasks involved in looking at community resilience metrics. They've identified over 100 so far. We're focusing on 5 of these. They're very much dependent upon the community. These are metrics that I think everybody agrees are important in most communities, and so we selected those for that reasons, to test our assessment and our decision algorithms. Note that those community metrics are community dependent, and actually most of them are actually based on social and economic factors, which means that the social and economic members of the team are actually, as I might say, driving the bus when it comes to determining the appropriate criteria which ultimately will be implemented to enhance community resilience. Thank you, Paula.
Thank you, Bruce. Next, I would like to invite Professor Wang to say a few words about her contribution.
Thank you, Paulo. Okay, this work introduces a community building portfolio analysis framework with an objective of supporting risk-informed community resilience planning. This framework includes the following components. We first start with a spatial and temporal hazard characterization at a community scale. And for Centerville, we'll focus on earthquake hazard. And then we move on to portfolio level damage assessment, followed by a functionality loss estimation. And that serves as a starting point of building portfolio recovery modeling. Ultimately, this quantitative assessment framework for building portfolios, together with those developed in other center tasks for different physical and socioeconomic systems, will collectively form the basis for risk-informed decision to support community resilience planning. So in this study, we addressed the following challenges: uncertainty propagation and spatial correlation modeling from hazard characterization all the way to decision support. Building functionality assessment considering availability of utilities. Building portfolio recovery trajectory and recovery time estimation. And finally, we ensure scalability of our analysis algorithm as we move beyond Centerville to larger communities. This analysis framework resulted in 5 building portfolio performance metrics. Immediate occupancy ratio, the percentage of a building portfolio that can provide safe occupancy immediately following a disaster. Household dislocation ratio. This is estimated by a household dislocation algorithm developed by the center social team and using building damage estimation as one of the input. Direct loss ratio, the ratio of total direct loss to total assessed value of a building portfolio. And then portfolio recovery index, the percentage of buildings that are in any of the 5 predefined functionality states at any given time following a disaster. And finally, we have portfolio recovery time, the time takes for target percentage of buildings to regain or re-achieve their full functionality states. In this analysis, we estimated not only the mean, but also the uncertainty of all those 5 metrics. And the Centerville special issue, however, focused on the first 3, and which have been incorporated in the in-core alpha version that Dr. John Lee will demo later. So as introduced by Professor Bruce Ellingwood before, the Centerville test building in portfolio include about 1,500 wood structures in 7 residential zones, 151 steel and reinforced concrete buildings in 2 retail and business zones, 70 steel buildings in 2 industrial zones, and about 19 reinforced concrete and masonry buildings for schools, hospitals, and fire stations. So we performed the damage assessment first to the Centerville building portfolio for the 7.8 earthquake scenario. We produced the damage, including the damage to structural components, non-structural acceleration sensitive and drift sensitive components respectively. Those information was passed to the center economic team to forecast the economic impact to the local economy. Then through a damage to functionality mapping, we obtained the building functionality states immediately following the events, which is the starting point of the recovery. Following the Centerville special issue, we have also developed a building portfolio recovery model for earthquake hazard, which can output functionality state probabilities at any time t following an event for different building types, portfolio recovery time and recovery trajectory, temporal evolution of the spatial variation in recovery trajectory, and finally, the uncertainties associated with the recovery trajectory. In our ongoing effort, one of our ongoing effort is to work with other center teams to ensure building portfolio analysis is properly interfaced and connected to the analysis of other community networks and systems. Thank you.
Next, I would like to invite Professor Nicholson to say a few words about his contribution.
Thank you. In this work, we are interested in analyzing how different building retrofit decisions might mitigate the effects of a disaster and improve community resilience. In particular, we're interested in allocating limited financial resources to retrofit building types in each zone of Centerville to specific code levels with respect to competing objectives, minimizing the direct economic loss and minimizing the total household dislocation. Additionally, we want to ensure that the retrofit policies that we consider take into account the resilience difference that often exists between different socioeconomic statuses. We add a constraint to the model to not exacerbate the existing disparity levels. Now, we do realize that community leaders don't have the authority to directly impose retrofit actions on privately owned buildings. However, for the sake of the study, we are assuming that direct or indirect incentives do exist and that they are effective. So given the baseline scenario in Centerville, we have a wide variety of building types, all at different code levels for both residential and non-residential structures. We estimated the ideal budget, which would be sufficient in order to be able to improve all buildings to their maximum code level. We, again, look at the same earthquake scenario, a 7.8 magnitude earthquake, and if we perform no retrofit, we expect a total economic loss of $856 million in Centerville, dislocating over 3,200 households. So we want to evaluate the retrofit policies and decisions that we can make under three different budget levels, low, medium, and high budget level that are given with respect to the ideal budget. So in particular, we look at what is known as the set of Pareto optimal solutions. Since this is a multiple objective problem, we don't have a single solution, that would be an optimal objective, but we always have to look at trade-offs between different solutions. Along the vertical axis, we have the one objective, the direct economic loss, and on the horizontal axis, we have the household displacement. Our goal, of course, is to minimize both of these. The white region is known as the infeasible region because we simply don't have enough money to simultaneously reduce the economic loss and the household that are dislocated into that area. The gray region is known as the suboptimal region because all of these outcomes are possible, but we can do better, and that is represented by the blue line. The blue line is called the Pareto frontier. The solutions that produce these outcomes cannot be improved on at the current budget level, but they do represent trade-offs. For example, policy 1 at the top results in the highest economic loss, nearly $780 million, but the lowest household dislocation of about 2,500 households. These both represent significant improvements on the baseline policy. However, we have alternatives. We could also consider policy 2. Policy 2, for example, drops the expected economic loss by $45 million from policy 1, but it does that at the expense of increasing the household dislocation. So while we do not intend to make decisions for the community leaders, we hope to quantify and support those decisions. The trade-off, for example, here between giving up $45 million in loss to keep 220 families in their homes, the question is that worth it? And we can't answer that question necessarily. The value of dislocation, of course, affects things like the tax base, economic growth, things that can be quantified by our friends in economics, but it also has a lot of elements that are hard to quantify. The quality of life, the stability of the family, and education. So while we can't answer these questions, the framework that we're providing, we hope, helps decision makers to pinpoint these issues. The competing nature within this problem itself is primarily based on how the money is allocated towards the residential structures versus the non-residential structures. The green line represents investment in residential structures, and the blue line is investment in non-residential. On the left side of the graph, we're investing more in residential, so we're reducing our dislocation, but we incur higher capital stock loss. And towards the right, we move our allocation towards non-residential, in which we have higher dislocation but lower capital stock loss. Now, if we increase our budget, the budget that we looked at previously is the blue curve here, the $52 million, the low budget. But if we increase our budget levels, we're able to reduce the infeasible space. So the red line represents the medium-sized budget, and then the green line represents the high level of the budget. When you increase the budget, you can change the shape of the Pareto frontier, and at the same time, the types of trade-offs that you're considering making. Additionally, the tool provides not only the estimates of what this Pareto frontier looks like, but it gives you specific details associated with zone level and building type granular interventions that should be taken to help inform good decision making. Thank you.
Thank you, Charles. The contribution of Professor Vandelin will be discussed in more details later in the webinar. So I would like to move to the following paper and invite Dr. McAllister to say a few words about her paper.
Thank you, Paulo. So I'd like to present the work that was done on modeling the resilience of critical infrastructure systems and considering the role of network dependencies. And the paper focused on a unified methodology for modeling dependent infrastructure networks using a probabilistic procedure. And in terms of resilience, the focus was on recovery of the system as a function of time at the community scale. And the methodology simulated both direct physical damage as well as other damage caused by cascading effects due to dependencies, and then modeled the recovery level of the network functionality. So the methodology is general and can be applied to other systems. In this paper, we illustrate it with an example of water and electric power networks. So the dependency of the networks was simply modeled through an augmented adjacency table, a likelihood table, and a dependency table, and this is really more for conceptual purposes. But first note that there are two networks in the graphic there, the green network 1 and the blue network 2, and then the lines between them are illustrating dependencies. So this adjacency matrix then is constructed as shown below. So the connectivity between elements in network 1 and network 2 are in the green and the blue boxes on the diagonal of the matrix, and then dependencies between these two networks are shown on the non-diagonal terms, which are pink and orange on this diagram here. This is then further supplemented with a likelihood table that describes the likelihood of failure of a node given the failure of a node in another network. So we create the dependency there as well. And then we create a dependency table that is the product of this table with the adjacency or connectivity and the likelihood of failure. So the probabilistic procedure is based on Monte Carlo analysis, and just briefly, the 6 steps are to generate the network model and generate a hazard for the network area, and then direct physical damage is assessed through fragility curves, which has a probabilistic component. And then there is an iteration where we also include the cascading effects due to dependencies of one network on another, And then we assess the loss due to both direct and indirect losses. And there's a repair curve as well, data, to predict recovery time for the network functionality. And there's an iteration that goes on between these last steps to within a specified tolerance. So to try to explain this now with a water network and electric power network, this again is from Centerville. The water network is on the top and the electric power network is on the bottom on the right-hand side. And areas designated with A, B, and C are where we have commonality, where the water node depends on electric power node. So this is where your dependency is designated between the two systems. And you see the adjacency matrix below is showing the connectivity for the water network and the electric power network, and then their dependencies on each other. And in this simple example that we did, we have either a 0 for no dependency, independence between these two networks, and 1 for perfect dependency. If a electric power node fails, then the water node will fail as well. So we looked at these two cases, perfect independence and perfect dependence. And this is illustrated at the right based on the function of the water network. So given the physical damage that occurred and the direct and indirect damage at time 0, how can we predict these systems will recover, both for meeting the water demand and providing adequate pressure to meet that demand over time? Based upon whether you consider the system alone, which is the blue line there, or when you consider dependency on another system. And you can see that the independent system recovers more rapidly than the dependent system, which intuitively should make sense. And even though the recovery begins around the same time, that dependency will affect the ability of the system to recover, and this is an attempt to quantify what that might be. So in concluding, we would just like to say that functionality is very important, and the delay in the recovery process with dependency can be quantified with this approach. It's very important in determining resilience that you consider the physical damage along with the operational aspects rather than considering them independently, and that the cascading failures can lead to increased recovery times that may not be accounted for if that's not included. And this method is considered modular in that it can be applied to any network and type of dependency. Thank you.
Thank you, Terry. Finally, I would like to invite Professor Cutler to say a few words about his contribution.
The objective of our part was to build an economic model that could talk to the engineering side. So we used a computable general equilibrium model, and this work is with Martin Shields, Daniele Tavani, and Sami Zaron. So here is just a flow diagram of our model. And what we had to do is create spatial characteristics because earthquakes or tornadoes hit different parts of towns in a disparate way. So we have to have the model be consistent with that. So on the left-hand side, we have households, and those are distinguished by income and also a spatial component. The right-hand side, the blue box, is the firms. And what we have is flows of resources going back and forth. And just to summarize real quickly, households will supply labor to firms. Firms will then, in return, give wage payments. And with those wage payments, goods and services are purchased. And then there's also tax payments going from households to firms to local government, and also services going back. And so we build this model to be sensitive to the geographical distinctions and also some time series properties. So here's another picture of Centerville. We've seen it several times this morning. What we've done here is we've divided Centerville into two parts. And this black line going down in a little crisscross is dividing the city into a west part of Centerville and also an eastern part of Centerville. And what we want to understand is that the economic model we built represents the spatial characteristics we have here. So as an example, zone 1 on the upper left-hand side, that's the upper income residential area where there's approximately 4,200 homes, and so we have modeled those homes and those residences to supply, where families live, and also they supply labor, they also buy goods and services. So these people in Zone 1 will shop in different parts of town. They may shop in Zone 9, which is the vertical pink area, or they also could shop in Zone 8, which is the horizontal pink area. And so we have all these shopping patterns in town, so when there's a disruption, people's shopping patterns may change, and also their ability to get to work may change. So what we do in the simulations in the paper is we divide up Professor Wang's earthquake into two parts. We just let the earthquake hit the west part of town, and then also separately the east part of town, to understand the spatial differences when different parts of towns are, different part of the town is impacted. Then we also look at some dynamic outcomes where we shock the entire town, and then we see the dynamic properties over time of how the town responds, and what this will be used for eventually is the recovery aspect in terms of the economic analysis. So we just do the east and west part of Centerville. We damage them separately, and I just want to highlight the first column of results, and I think that highlights the uniqueness of building a spatial CG model. So when the east part of Centerville was damaged, there was an employment loss of 161 workers and an output loss of $15.4 million. But the important result is west part of Centerville actually benefited, because they weren't damaged, so people who no longer could shop in the east part of town because that was damaged would then shop in the west part of town. So there was actually I shouldn't say a boom, a slight increase in economic activity. But when the west part of Centerville was damaged, where a lot of the economic value resides, west part of Centerville fell by $34.3 million in economic output, but also east part of Centerville was damaged, because that overwhelmed some of the travel patterns that would occur as people tried to shop in the east part of town. The losses were large enough in the west part of Centerville to actually cause an entire downturn in the town of Centerville. So it really highlights, as the earthquake hits different parts of town, we get very different results. We also have some dynamic outcomes, and the green line represents the damage to the capital stock, and then the way the economic model works, when capital is damaged, firms will substitute into labor. So we can watch over time as the downturn in the first period to capital stock, then the green line starts to rise, and that has to do with the substitution of out of capital into labor. And that's an important substitution practice in our model. But then when you damage the transportation network, which slows down commuting times within the city, we see that that's the red box, and we see a decline in that, and there's a permanent loss in economic activity, because the economic literature suggests that damages the transportation network actually reduces total effective productivity for firms and can have a permanent loss in the economy. And the third line is just a combination of two, which is not worth going through right now. So to conclude, we've established that building a spatial economic model is incredibly important. And to further that, in our Joplin model, we're putting people who commute in and out of Joplin. And we'll do that also for Shelby County. So commuting patterns are also incredibly important. And then these dynamic patterns of the CG model can also be used to help model recovery. Thank you.
Thank you, Harvey. This concludes the overview on the special issue of sustainable and resilient infrastructure on the Centerville testbed. Our next speaker is Dr. Lee. He's a principal research scientist at the National Center for Supercomputing Applications at the University of Illinois at Urbana-Champaign. He will give a presentation and demo on InCore.
Thank you, Paulo. So I'm going to show you how the InCore implementation can happen with the oldest paper, the presentation you already saw. So I'm not going to explain the science behind it, because you already had this presentation. So these are the demos I can show you. And then these are the demos or actual analysis we built on the InCore analysis. We work with the authors. They implement their code and their data ontologies and data sets on the InCore system. So we're going to go over the building portfolio analysis and electric power network damage analysis due to the tornado, and water network recovery analysis with the EPN, electric power network dependency, and mitigation resource allocation analysis, and then at the end, the computational general equilibrium model analysis. First one, I want to just make a note that if you already recognize that all those research is done based on certain scenario earthquake or scenario tornado, a certain scenario hazard, the good thing about you implement those algorithms on the platform is after you implementing it, you are able to change some of the scenario hazards. So now you are able to see that those analyses in the paper, how you can actually use it with a different scenario of hazard, different earthquake, different tornado, things like that. So for example, the building portfolio analysis, right now, we're going to show you that how it's calculated, but you see there's a little red box shows create scenario earthquake. So you are able to create your own scenario related to Centerville to see that how this building portfolio analysis performed based on different hazard. So this is the video clip of the demo. Originally, we planned for the live demo, but there are some technical difficulties, so we're going to show you the video clip. So right now, what you see is actual Centerville building data we created randomly for this exercise. And you can see that you click on this analysis, you need to give them some result names. Now you are able to pick building inventory data. And then this is the one I just told you that you are able to create some Centerville earthquake. This case, we used the one we created before, but this one is especially using the liquefaction. So with liquefaction, without liquefaction, can give the building damage totally different. And then now you're able to see that all those parameters relate to the paper. So we turned some of the information in the paper into data set. So now if you want to tweak the model, you're able to change the data set and you can have a different models too. Now we picked the zone Z1. Zone 1 contains residential area. And then for sake of time, we only do the 100 iterations. And you execute, it calculates building portfolio analysis. It's going to show you 3 metrics as a result. For sake of time, I will skip a little bit. And then after you finish it, you can see that those tables are generated, which you can find in your those paper too. So this one, you are able to also create a chart. Let's create a chart for direct loss ratio. Now, x-axis is going to be probability of exceedance, and then y-axis is going to be your direct loss. Going to select the direct loss ratio, and then line chart, and then create. And then you are able to see this chart similar as your paper. This one is a little bit jigged because we only run the 100 times of iterations, but if you choose 1,000 times, it's very close to how it looks like in the paper. This is a household dislocation ratio chart. And the next one shows immediate occupancy ratio chart, similarly. Okay. Next analysis is electric power network damage analysis. This one utilizes in-core scenario tornado. We actually showed you last time. So you are able to create a scenario tornado with the various kind of settings if you want to. So we're going to utilize this scenario tornado to compute the damage of electric power network. Similarly, now we select the electric power damage analysis due to the tornado and give the result name, and then select Centerville power network. You already saw a couple of times in the previous presentation, and we're going to create a scenario tornado. So methodology, we're going to use a mean width with the EF5 rating, and you pick the beginning and ending point of the tornado. And then now you run the damage analysis. Then what happens is it runs a scenario tornado analysis and then run the power network analysis sequentially. So you're able to see now, and then the result looks like this. So you can see that there is a tornado generated from our scenario tornado analysis, and you can see that the power network facilities have some damages. And these are those tabular form of the damages you are able to look at. and you are able to also export and do some further analysis if you want to. Next demo is water network recovery analysis. This one is the most complicated one we encounter because of two reasons. One is the dependency, because we encounter the electric power network dependency on this analysis. You are able to turn on and off the dependencies to run the analysis. At the same time, water network itself composed of two parts. One is water facilities and also water pipelines. So we do those analyses separately. So you can see quickly here that here is a water network recovery analysis. There's a buried pipeline damage analysis, and here is a water facility damage analysis. If you turn on the dependency, then there's another box shows up for power network damage analysis too. So here is a demo. For your information, in order to run like a 800 iteration is actually written in the paper, it took about 2 days. So we only does that short iteration here. So you can now see here, you can see that the new analysis popping up. So this one is a water facility damage analysis using the Centerville water facility. And now you also create the scenario earthquake for this. We're going to show you. So we're going to use Fernandez and Rick's attenuation, and then also you are able to pick the epic center. And this time I believe we also use liquefaction. So right now we picked the liquefaction susceptibility map in the Centerville. And the next is we're going to add the buried pipeline analysis for water. It's a similar way to give the result name, and you need to pick also Centerville pipeline, water pipeline, and use the same earthquake, scenario earthquake. And you can see that it's sort of connecting each other. And then IMP file is actually EPA net file, actually allow you to do EPA net analysis, demand flow analysis. So this one is allow you to do day by day, even hourly, how the flow changes behind the water network analysis. And you can see that because we turn on the power network dependency, now you can see electric power network damage analysis shows up. So all those things now connected. Now you click, you need to change the iteration number, right? So we're going to do only 3 runs, but you can actually increase 800 if you want to. So now you run, let me skip a little bit. After you finish it, then now you are able to see some result here. So we're going to show you, there is a statistics summary of this analysis. It shows you the average demand, average pressure, average contamination in the water, how the recovery happens, and how this value changes throughout the time. So you can see it like this. So x-axis is the days, and while the time changes, it recovers, and also those values are changes. You are very easily see in this way. Or if you need a further analysis, you can also export the data set into Excel or CSV formats. You could do further analysis. Next analysis called mitigation resource allocation analysis. This is a multi-objective optimization. As the chart shows you, there's a Pareto, the solution, which is a multiple solution strategy you can have. So a good thing about this implementation is users are able to actually click on those solutions and tell you what the detailed solution is. So I will show you for sake of time. It's a very similar way to do. I'm going to skip to the result part. So you can see here output, you can see that on the Pareto front, and click on those solutions, it shows what the solution looks like. The solutions shows that which zone, which building type, and which code level, and how many building needs to be that one, so that it will tell you exactly how solution looks like. This is the data behind it. So we visualize this data onto that user interface. Next one is a CG model, CG analysis. this model also a very complicated model. However, we implement this on the web service instead of we actually running on our in-core platform right now. In other words, in-core platform able to talk to the web service we build so that actual analysis happen on the server side, and we only retrieve the output from the analysis. And we know the CG model is very complicated. But we only expose some simple table output right now, but in the future, we're going to expose more outputs from the models for needs. So especially this table you see is corresponding to the paper, I believe, with table 6A. So we are able to generate exactly the same table from it. Differences from the paper is this one also you're able to do the scenario earthquake and do the building damage analysis. Because paper itself has a scenario earthquake, the fixed, and also use a fixed building damage analysis. But this case, you can actually change that and also change the mapping if you want to, so that you are able to see how the CG model performs based on different scenario earthquake. For information, it takes about one hour to run, so we're not going to show you how actually running. But it's really worthwhile to see that how we can connect the new analysis with the existing analysis we already built. So CG model here, and then CG model needs some external shock, which is of damage, building damage. So building damage need to be aggregate to the sectors and zones within the Centerville. So right now, you can see middle box does the aggregation. And this one is building structural damage analysis. So we use exactly the same building damage buildings used in the building portfolio analysis. And then we pick earthquake. So this case now you are able to pick which one you like. So you can also pick the epicenter on the map. And you can change also magnitude if you want. And also this time you also use liquefaction for the building damage analysis. So when you execute, what happens is it creates a scenario earthquake and then run the building damage analysis for each buildings, and then it aggregates building damages to the by sector in the CG model and by zone. And then it generates the vector table for the CG model and plug into the CG and run the CG model. So I'll skip to the end. And after you finish, which in the server side, it's going to retrieve that output to the platform and shows some of the output here. So I'll skip this one. So this is a vector I mentioned to generate for the CG model. And then this is a result from the CG model, shows the table, that how the changes happen between different household and different household classifications. That's end of demo. Thank you.
Okay, thank you, Jung. So at this point, we have 10 to 15 minutes for questions and answer. If you would, if you've not already, if you would like to email those to Professor Hussam Mahmood, who will select questions, and the email address appears on the screen. It's hussam.mahmood@colostate.edu.
So we don't have questions yet from people watching the webinar, so I think we could start with the group here, see if we have any questions. I'm sure we have a lot. Questions? It's not an option. You have to ask questions. I'm just being really nice.
So yeah, so I actually do have a question for Jung. So I don't know if you have a microphone, Jung, but my question is for InCore for the CGE analysis. You mentioned that it talks to a server and comes back. How I guess what is the level of effort required to actually ingest the open source CGE that's being developed within the center and how does that process unfold?
Oh, thank you for the question. Right now, Incore is open source platform, and initially when we work with Harvey's group using the commercial software, and then we discuss, and then thankfully the Harvey's group already found some open source solution to solve the CG model. So what happened is their group developed that code in a Python and actually sent to us, and then we modify a little bit to fit into our web service and running on the server. And also I got the email that they found another server that running much quicker, so it's not an hour. So I think this is a process I think we're going to have, working with NCSA developers, with the researchers, to find out and helping each other to improve the performance and also improve the way to modeling their researches. Does that answer your question?
A question back there. This would be a question really for any of the developers. Bruce mentioned uncertainty, and I wonder if any of them could talk about the plan to get error bars and uncertainty into some of the graphs in the analysis. Who's going to address the question?
Well, Jason, I don't know that I'm the right person to answer this question because I'm not one of the developers, and I think your question was directed to the developers. But my general answer to your question is that I think we have to get the physics of the process right before we start propagating uncertainty. And I think we're there on many of the models that we've incorporated in Incore. We may not be quite there on some of the other models. So there is, in fact, a task on uncertainty propagation and analysis, which Paulo and I are working on. And it's kind of running in the background with all of this because we really can't do very much with that until we're confident that the models that we've already developed are correct in capturing the basic physics of the process. So the short answer to your question is I think that that's one of the things that we're going to be probably increasing the emphasis on in years 3 and 4, particularly as we move toward a risk-informed decision model. But we haven't, by design, focused on that aspect of the problem right from the get-go because the models that we're using, to the extent that we can make them so, are physics-based rather than purely empirical. So there's no point in trying to do an uncertainty analysis until we've got the models properly developed.
So just want to follow up on the uncertainty modeling question. In the building team, we do emphasize uncertainty modeling. In those 5 metrics that we're trying to quantify, we analyze both the mean and the uncertainty associated with the mean. And we believe this uncertainty quantification is the basis for risk-informed decision. And those uncertainty modeling right now, the information we passed on the social and economic team is the main information because that's the analysis they're doing right now. But in the future, we're hoping that the uncertainty quantification we did in the building analysis also can be utilized in the decision making. And also the 3 metrics that showed in the demo, those curves, they are actually the CDF or the complementary CDF of the 3 metrics. So they are the uncertainty measure. Thank you.
Thanks, Naila. We have a question from Joshua Stillman at University of Nebraska. The question is, how code levels determined and/or modeled for tornado and flood hazards? How are code levels determined and/or modeled for tornado and flood hazards?
So, okay, well, first, thanks for the question. So the tornado hazard, like many of you know, right now the tornado is simply an ASCE 7 is just a commentary. So not so we're not designing for those yet. So For the tornado hazard levels, it's as you heard Jong Lee mention with respect to earthquake and some of the other hazards, it's really scenario based. So it's based on what the community leaders or the constituency within the community, what they feel they should be designing for. And so there could be one, there could be more than more than one. It could be that they have, and so one of the resources to kind of investigate that a little more would be to look. There's a NIST planning guide that was led by Dr. Terry McAllister, and if you go to the NIST webpage, you can take a look at the 3 different levels of hazard to be considered for resilience. And so I would, I guess, suggest that as a good reference, as a starting point. For flood, I guess I would say, I guess I'll punt that one to someone else if they'd like. But. Oh, same question, Bruce. Just with respect to code levels, I guess BFE and things.
We're not, we haven't done an exhaustive analysis of the response of the built environment to flooding yet. That will come in the Memphis Metropolitan Statistical Area testbed, which we're starting in and working on this year. As far as Centerville is concerned, the building portfolio in Centerville actually represents construction over the past approximately 100 years, with an emphasis on construction that occurred following the Second World War. And so as far as the different code levels are concerned, the way that the fragilities are modeled in that portfolio or in that study are dependent upon when the building was designed and constructed by what code. And so in that particular sense, we're covering kind of a broad range of design criteria rather than one specific design criteria.
Thanks, Bruce. We have one more question. These tools all look very helpful for government decision making, but I'm curious if the presenters think the model input data is readily available from local governments or private utilities. In short, from the presenter's perspective, what is the feasibility to input real community data into the model? Sorry.
Thank you for the question. And data is a question that the whole center has been talking about, and it is a very important point. And I would say that we're looking at what data is publicly available. We recognize that some of the data communities will not want to make public, but if they do their own analyses, they can maintain the privacy or security of that data. And we're hoping this analysis will make people aware of the type of data that needs to be available or collected. It's not all available right now. So that is part of the research aspect of what we're doing. Thank you.
Thanks, Terry. Here's a quick one, and then we'll take questions back from the audience. What is the projected release date and availability of NCORE?
It's a great question. I was hoping for that one. At this stage, we will be releasing an alpha version within just the Center of Excellence. I know the question comes from outside of the center, and that's for debugging purposes. So some of you already have it from the training session last night. We're targeting the end of summer. So about 4 months. That will depend, on bugs and making sure that intellectual property and things have been, papers have gone through the review process and things like that, the related papers. Now, the papers you just saw, of course, are all published in that 2016 special issue. So we anticipate the end of summer, but that's a target date at this point. But if you check back to the web page, we'll definitely be able to update that, I'd say probably in 8 or 10 weeks.
All right. Questions from the audience? This group is not too active. Okay. I'll let it pass this time. All right. So we'll move on, and I think now we have the Joplin Hindcasting, and I'd like to introduce Terry. She can start the discussion.
Thank you, Hussam. So I'm just going to introduce the 2011 Joplin Tornado Hindcast work, and John, Professor Van der Lint, is going to present the work that was actually done by the center in collecting data along these lines. And you can see it's a very large team. We actually went to Joplin to collect this data in the last year as part of understanding the recovery process. So today I will just do the introduction here on what Joplin tornado looked like, the damage that occurred, and a short, very short summary of the investigation that NIST did. And then the rest of the presentation will be on the field study data that was collected. And you see the focus here on the electric power network and buildings, including their dependencies and functionality, and inclusion of business interruption and vulnerable populations. So in case you're just wondering what hindcasting is, it's a systematic process to check the accuracy of our models using a past event. And for Joplin, we'll do this both for individual buildings and components and aggregate those into system levels. And this will be done at points in time to validate damage modeling, loss estimation, population dislocation, and then functionality and recovering over time. So about Joplin, Missouri, it has about 35 square miles. Its census population is about 50,000, but because many people come into this community from the surrounding area, it can swell to 3 or 4 times that level in the daytime. They have about 23,000 housing units, and the median value of these units, of the houses, are about $103,000. So into this community on May 22nd, 2011, the Joplin tornado occurred. It reached peaked EF5 intensities. It resulted in 161 fatalities. Over 1,000 people were injured. And it was the most expensive tornado in U.S. history to date, with losses at $2.8 billion. So it touched down about 5:34 on a Sunday, and it stayed on the ground for 22 miles and 15 minutes. 6 miles of the path were through the city of Joplin. Based on the damage, it was rated to be enhanced Fujita scale EF5 tornado with maximum wind speeds over 200 miles an hour. This ended up destroying about 1/3 of the city's buildings, and 40% of the city's population was affected. With the fatalities, this was considered the single deadliest tornado on record when you look at tornadoes, hurricanes, and earthquakes. And the official warning time to the community was 17 minutes. The national average is 14 minutes. And you can just see in the diagram here below, the red line is indicating EF4, that very dark line, EF4 and 5, I believe, and then the shades go out showing the less intense wind speeds as you get away from the center. So NIST, with the fatalities and the damage that occurred, deployed an investigation team and conducted a technical investigation. The objective was to determine the tornado hazard characteristics and associated wind fields, the performance of the buildings, including shelters and safe areas, and the performance of lifelines as they supported these buildings, the pattern, location, and cause of fatality and injuries, and associated emergency communications and public response. And finally, areas and current codes and standards that might warrant revision. So the report actually had 16 recommendations and a number of findings. There's not enough time today to go through this, but here are 4 findings that set the stage for the work that you'll see in the following slides. 40% of the fatalities and as much as 90% of the tornado damage area were associated with EF3 or lower wind speeds, and that's about 160 miles an hour. Of the buildings damaged, 7,400 are residential and 550 were non-residential. There was engineered structure, St. John's Regional Medical Center. It had the building envelope damaged. There was very little damage to the structural frame, but it ended up losing all its functionality due to the damage to the building envelope, and ended up being declared a loss. All the utilities, water, gas, and power, were lost in the area were most damaged, and they had their service restored to critical buildings within 24 hours. And it was a great example of how utilities can work with the local community to prioritize the type of restoration that's needed. So with that, I'm going to turn this over to Professor Vandelent.
Thank you, Terry. So critical to the successful hindcasting is the need to gather data for comparison, both damage and recovery data. For Joplin, this was done by a team of researchers, as well as NIST, which you just heard about. Photos are automatically geotagged and hyperlinked to a map for future comparison to photos during and following recovery in the past 5 years. So recall that for hindcasting, we begin with each sector model independently in order to better understand the model resolution needed, but also what's available. And this perhaps comes back to the question that was asked, what can be provided or what would be provided. In the case of Joplin, a detailed model of the electric power system just prior to the 2011 tornado was provided to the team in order to predict damage to the system. But recall from the introduction to the webinar that a generic and simplified tornado wind field was proposed for community resilience studies. In this initial hindcast, and so this is really just our first step, we use a curved wind field model, which is more representative of what was in Joplin. Now, it's important to keep in mind that for a full model validation standpoint, from that standpoint, this wouldn't be acceptable, but it is acceptable if we're trying to isolate the accuracy of just our fragilities in predicting damage as a function of wind speed spatially. As you can imagine, there's numerous complexities to hindcasting to ensure that current knowledge is not incidentally applied and biases the prediction. So modern electrical power distribution is versatile in providing service coverage, which makes it actually much more difficult to model. One of the key aspects of the center is importing algorithms and methodologies when they fit the needs of the analysis. But there is substantial new development also underway. The results of a study from approximately 15 years ago at Los Alamos Labs was applied to use weighted cellular automated to identify electrical service coverage areas. This figure isolates a prediction of just the pole and transmission line damage for the EF2 rated region. So what this means is anything inside this path that you see, the black inside, is EF3, 4, and 5, but it's not shown here. So for the full electrical power network prediction, a total of 113 transmission towers and about 3,740 distribution poles would be badly damaged. So how does this compare with what was observed following the tornado in 2011? That was 135 transmission towers and 3,850 poles that were badly damaged or collapsed, or destroyed, I should say. Modeling all the physical components within a community's infrastructure is a significant task, as anyone knows that set up a spatial earthquake model, and certainly they can attest to that. However, unlike earthquake fragilities, building fragilities for tornado loading are quite scarce. So one of the joint efforts for the buildings task team and the Joplin Hindcast team was to develop a portfolio of buildings representative of a typical community or a city. It was decided that a minimal portfolio of 19 buildings would be used and essentially provide analysts the ability to differentiate between critical attributes affected by wind load in a tornado. Obviously, a community has hundreds of building types, but the key here is not to model each building individually, but have a fragility for damage and recovery of functionality that's accurate enough to interact with other physical and non-physical components in a community level model. The fragilities range from 6 different residential structure fragilities to heavy industrial facilities to schools and community centers. A typical community can have tens of thousands or more buildings, making assigning fragilities a formidable task. In addition, it's critical to be consistent in the assignment of these or any functions. Although not presented in detail here, the center has adopted the GEM taxonomy, which is being extended from earthquakes to other hazards. Here we see a snapshot of the tornado taxonomy, which begins with level 1 attributes such as enclosure classification, height, roof shape, and other building attributes that affect wind loading intensity. Then level 2 attributes provide better information upon which to characterize the building and assign fragilities. For vertical load path continuity, this could, for example, be a full roof to foundation load path. Once the 19 fragilities are assigned to the buildings in Joplin, the probability of each building in a damage state can then be determined. For example, in damage state 1 that you see, damage state 2, 3, and then a damage state 4. The computation is performed using an algorithm to convert the building to a point, and then it's converted back to its original geometry in GIS, as shown here for damage state 4. Then for a multi-sector validation of buildings and the electrical power network, both sectors can be combined. This image, which shows all the buildings in Joplin color-coded, depending on which of the 19 fragilities was assigned to them, and then also it shows the lines, which are showing the power transmission and distribution networks. Here we see the CA algorithm with both sectors represented. This work is ongoing, and at this point, damage to buildings, the power network, and their functionality interaction can be modeled. A 4-step probabilistic post-disaster functionality methodology has been developed to be applicable to any building type and hazard. This methodology integrates performance-based engineering concepts within the context of community resilience for buildings and combines them with repair and functionality analyses to allow quantification of building functionality through a series of Monte Carlo simulations. This methodology is illustrated through the example of 3 building types identified in the Joplin community building stock, namely a school, a heavy industrial facility, and a strip mall, with the assumption that these are in building damage state 3, or what we call extensive damage. The intrinsic functionality fragilities, accounting for only construction and cleanup time, as well as the semi-intrinsic functionality fragilities, accounting for additional external factors, such as time to obtain financing and permits, are generated to quantify the probability of the building's post-disaster functionality. It can be observed that post-disaster functionality levels differ for the 3 building types depending on their construction details as well as their occupancy type. In addition to the hazard intensity, the continuity of businesses following a disaster are affected by factors internal to the businesses, such as decisions on business operation, capital investments and cash flow, supplier and labor availability, and customer demand. Passive business characteristics, such as employment and line of business, also affect the impact and recovery. External factors affecting business interruption and continuity include utility lifelines, transportation networks, and telecommunication, to name a few. Policy interventions such as insurance and government assistance also affect the short to long-term recovery outcomes. In order to estimate the probability of business closure 3 months after the event, the interdependency of physical structural damage and business characteristics is modeled. And I see we're using a Mac. This was developed on a PC, so I see we have an equation problem, but we can get you that equation if you're interested. So, first, the expected damage is estimated by calculating the sum of severity of the damage at each damage state, weighted by the probability of each damage state, each of the damage states. Then business characteristics such as employment size, franchise status, and sectors including manufacturing, construction, and retail are considered. The map at the top shows the probability of business closure at each business location. As would be expected, the business closure tends to increase as the tornado intensity increases. No businesses were predicted to have closed in the EF1 region of the tornado. About 6% closed in EF2, 77% in EF3, and above 97% of the businesses closed in the EF4 and EF5 regions. The total jobs affected were 945, and total annual sales value affected is predicted to have reached over 176 million. Although just under development, a computable generalized equilibrium model similar to the one you heard about for Centerville will provide a measurement of the economic impact the tornado had on Joplin. Predictive models for each year will be developed to determine how well the forecast predicts changes to the local economy. Population data from the Census Bureau is used to determine the spatial variance and social vulnerability. The social vulnerability perspective focuses on the social factors and processes that generate vulnerability in terms of an individual's or group's capacity to anticipate, cope, resist, and recover from the impacts of hazards. Social vulnerability is not uniformly or randomly distributed within our communities, and therefore it's important to know where socially vulnerable populations are located. Previous research has used county level and census tract data to explore this question. The INCORE process is using census block groups to process or provide a finer resolution, which is important for hazards such as tornadoes, which impact a much smaller geographic region. This slide compares the resolution provided by census tracts and census block groups for Joplin, Missouri. The areas shaded in orange and red have a higher index value of social vulnerability. This slide provides an example of why using a finer resolution such as block groups leads to more accurate assessments of vulnerability. In the case of the 2011 Joplin tornado, the fact that the tornado path was through areas with higher population density helps to highlight one of the shortcomings of census tract data. In general, the larger resolution assumes lower levels of population density and leads to an overall undercount of the population. The undercount is even greater for socially vulnerable populations, which were more highly concentrated in block groups impacted by the tornado. Over the next 6 to 9 months, other dependencies will be added to the predictive models. Recovery functions have been developed and will be assigned to buildings and other components within the infrastructure, attempting to take into account permitting and financing. Each of the algorithms presented earlier for Centerville will be applied to Joplin to test their ability to predict physical and socioeconomic changes to the community and eventually recovery. So on behalf of the entire Joplin Hindcast team, and it is a large team, thank you for your attention, and a special thanks to everyone who welcomed us if you're listening out there in Joplin last summer. I'd now like to introduce Judy Matrani-Reiser, the head of Disaster and Failure Studies program at NIST, and our social science lead for the center, Walt Peacock, to give a presentation on Lumberton.
Thank you, John. Good morning to everyone here and out on the web. I'm very honored to be representing a very large collaborative team that went out into the field together a few months ago to study the impacts that Hurricane Matthew had on Lumberton. I wanted to start by describing the thrust area for field studies within the center, and then also describing the role of field studies within NIST, and then combining that together so that you see the strength in leveraging these two efforts and jointly going out into the field together in future deployments. So as John mentioned earlier, one of the big thrust areas for the center is on field studies. The purpose of this is to validate a lot of the modeling and inform a lot of the models that are being developed from the center. In order to measure communities' resilience, the center plans to collect metrics that can be divided into two major categories. One that require field studies. These are metrics that you cannot just go out and collect and hope to find on the web. They're not publicly available, so you really need it to go out into the field and collect them yourself. And so some examples of these types of metrics are population dislocation, so looking at households that have been displaced, business interruptions, businesses closed and their recovery over time, employee dislocation, employees failing to report to work, critical facilities impacts, so the closure of critical facilities after a major event, and housing units lost. Now, to support a lot of these metrics, you can collect data that doesn't require field deployments, such as physical and mental morbidity, mortality, and fiscal impacts, so loss of property tax and sales tax. Now, the community dimensions that are described in the Community Resilience Framework, a report that was put out by NIST, includes many more dimensions than the metrics that I'm including here, right? So that report shows the importance of sustenance and health and shelter and education, security and safety, culture and identity, and belonging and relationships as being vital to community resilience. And so while these metrics are not explicitly being collected out in the field yet, they are embedded in those metrics that we are collecting. All right, so that gives you some background on the role of field studies for the center, and I want to, in parallel, give you some background of the role of field studies at NIST. So NIST, for almost half a century, has been studying and investigating disasters and events and deploying teams into the fields and looking at the impact that structural failure has. And so part of the disaster and failure program, which I direct, has a statutory arm to it that's described by the National Construction Safety Team Act. And so we have an obligation when there is an event that rises to the level of being investigated, that we have go out, study the impacts of this failure or disaster, and then give recommendations to the American public on how we can prevent disasters like this from happening again. That's one arm of the program, are these types of the statutory arm. Another part of the program is developing standard operating procedures for field deployments. So, as you know, standards is in our name, and so we like to have standard procedures when we go out into the field, and that includes a number of things. So, you know, how do we standardize when we decide to go out? What are the field and safety protocols that we're using as a team when we're out in the field? What protocols are we using for human subjects research? The protocols for equipment and data preservation, all kinds of things that we're really trying to standardize so that every deployment that we go has a lot of consistency, and so that others that deploy might want to look to our standards and maybe mimic them for their own type of deployments. And then the third part of the Disaster and Failure Studies program at NIST is really focused on the research arm, and this, I would say, encompasses the Organic Act, where we've been deploying to investigations for half a century. And so this is looking at what are the research questions that we're learning from investigating and studying these events. And now we have exciting opportunities to collaborate with the center, with other federal agencies, and through a lot of outreach work to grow this research program for DFS. So in marrying these two programs, I see a huge benefit to our communities. So the two programs are really going to benefit in three major areas: in data collection, in field methods, and in findings. So we'd like to collect data that establishes likely technical factors that are responsible not just for poor, but for successful performance of building an infrastructure, right? So we want to capture when we're doing things the right way, and build that into our thinking. We also want to collect data that's related to community impact and recovery, which has not been historically done in NIST investigations, but I believe will be a new and exciting direction that we're moving in with, especially with our new, we have new groups on community resilience. Collecting data to validate models that are under development, and this is really key. So a lot of people are developing models right now that are related to community resilience, and we need to do some work to ground these models. And these field investigations are going to give us the opportunity to validate at least and inform a lot of the modeling that's not just going on here, but going on in so many other research groups across the country and internationally. Second, area that the collaboration is really going to inform is on field methods. So trying out new field sampling protocols, this is really key. I mean, we did something really novel with Lumberton, and I hope that can be repeated with future field investigations and future groups that are going out there. And also assessing new field equipment. So these opportunities, when we go out together, it's really a nice opportunity to try out new things, see what works and what doesn't work, and then update how we might incorporate those types of equipment in the future. And then finally, what our findings are going to do, what kind of implications might our findings have. So we'd like to recommend frequency of data collection to capture community functioning over time, right? So we're learning from this process. We're going to learn what's the right frequency that we have to return to a site so that we can truly capture its recovery over time. And also recommend, as necessary, specific improvements to standards, codes, and practices based on field studies. So when I started at NIST about half a year ago, Hurricane Matthew happened about a month after I started, and I would say John called me immediately, and we started talking. This was a very big event. At its peak, it was a Category 5 hurricane, so we knew it might have the potential impact to be a very interesting disaster to study. And so it hung out at the coastline for a while before finally making landfall as a Category 1 with sustained winds of 75 miles per hour in South Carolina. But it had very large impacts, especially to the state of North Carolina. We saw 27 deaths in North Carolina. More than 2,300 people were saved with over 600 rescue operations. Thousands were displaced. A lot of people at its peak, 900,000 without power, huge transportation and network disruptions, and more than 40 schools closed for 3 weeks. It's a long time for kids to be out of school. So North Carolina became a focus for us as a potential interesting study area for community resilience reconnaissance work. And then we started looking at specific counties and trying to find one that would serve multiple purposes. And so we finally focused on Robeson County for many reasons. It has a very unique population. If you look at the demographics, it's almost a third white, a third black, and a third Native American, mostly Lumbee Indian. And that was very interesting because if you want to look at societal impacts from a disaster, looking at a heterogeneous population is a nice starting point. Also, there was the hurricane and the subsequent flooding had huge impacts on this area. Over 5,000 were displaced, over 7,000 structures were impacted, a lot of customers, 5,000 without power, a lot of roads were impacted or damaged, and a lot of damage to public housing developments, totaling 545 units. So the impacts and the demographics of Robeson County were really compelling to us to make it a study area for our joint effort. And the school closures specifically, the population dislocation and school closures were of special interest because those are two areas that are of interest to the center's research goals. So we decided that we wanted to go down there and assess the damage to school buildings and the impact to the educational system and use that as a driving force to choose the housing units that we decided to look at in terms of damage and reasons for dislocation. So we used that as a starting point for sampling protocols, which Walt will present in just a second. The second study objective was to study how the floods impacted the housing stock and collect empirical data to compare with existing fragility functions. So updating and providing to the community new fragility functions is really critical, and this study helped do that. And then finally investigating the dependency that these important community functions, housing and the educational system, have on distributed infrastructure networks such as power, water, wastewater. So this is a picture of the advance team that went out into the field. There were many of us, and I'm going to turn the presentation over now to Walt Peacock, who's going to describe to you all of our efforts while we were in the field and where we are now in terms of analysis. Thank you.
Thanks, Judy. This is, again, a picture of our field team, or our initial field team. We actually were there for over a week, so we had people coming in and out in terms of participation in the field. This really gives you a better picture of the number of people that were involved. And the really neat thing is we had 7 different universities that were involved, as well as individuals from NIST and FEMA that were involved. And importantly, these were social scientists, economists, planners, as well as sociologists and engineers linked together in interdisciplinary teams to try to address and understand what happened with respect to Lumberton. So to kind of focus the specific activities from an engineering perspective, it was damage assessments of a random sample of housing units to inform our fragility curve development. From the social science perspective, we were interested in interviewing households themselves, the households that were occupying those housing units, to inform our population models, in particular focusing on dislocation and displacement within the community, and then combined engineering and social science goals with respect to, and this was engaged in terms of a qualitative survey of community leaders and stakeholders to understand the impact, the response, and the long-term recovery and planning that was going on within the community. To get all that done, we had to go through institutional review boards, and for anybody in universities, these are one of our favorite boards to deal with. In this situation, we had 7 different universities in which we were trying to kind of get all of our protocols through. In other words, for our semi-structured, for our structured interviews, for our damage assessments, for how we were going to take photographs and what we were going to do with those photographs, we had to develop protocols to do that. And Jen Tobin-Gurley and Lori Peak were really the spearheads of this to really push these things through an umbrella agreement here at Colorado State and then through our universities. So we developed protocols in terms of the recruitment of interviewees, informed consent, the data collection methodologies and instruments, in particular the interview instruments themselves, what kinds of data that we were collecting, and then in terms of photography, both the public kind of photography that we would be taking of outside structures, as well as internal and getting clearance forms and releases and the like. And amazingly, it got through, and we were able to get out into the field to actually collect data. Now, a critical element of this was we wanted to capture, again, what was happening in that community. And so developing a representative sample, not only of housing units, but importantly of households, was critical. Again, our target area was the schools. So the boundary on here, the black boundary, represents the largest school district, the attendance zones for Lumberton Junior High. We wanted to make sure we sampled both heavily as well as lightly damaged, and even areas with no flood damage, but had infrastructure disruption and everything, so we can actually capture the full spectrum of what might be driving dislocation. So we developed a random sample here using a stratified 2-stage random sampling process. First, selecting on the basis of census blocks, which are critical for us to actually plot through what pre-existing population was like, as well as through the post-disaster process. And then randomly selecting within those blocks housing units. And this is just a map of the area with the census blocks, and the you might not be able to see them too well, but the dots represent then housing units. To actually implement this, we used Google Maps, and we actually identified then where every single housing unit was located, where the structure was, and we divided those up into areas, and everybody then had them on their smartphones. We didn't buy smartphones for everybody. Everybody already had their smartphones. So we had their smartphones, and so we can actually zoom in and then update these so we could mark where we hadn't surveyed, where we had surveyed, what was the state of the survey in those areas, as well as our primary and secondary units as well too. This is just a close-up, so it gives you an idea of how specific these maps were, and we could use them in a very easy way to actually navigate what was to the community itself and to get out there and do our surveying. We also updated this, so the maps were constantly updated, so we actually knew, again, where we were, where we needed to go to help in the overall planning process. We were there for about a week. Each day we began with briefings of where we stood, divided up into both the qualitative as well as the quantitative survey teams. assigned areas, split us up into our interdisciplinary teams, and then sent those teams out. Checked in at lunchtime, see how things were going and the like, as well as then in the evening a major debriefing in terms of where things stood, what people were seeing out there, what we needed to do for the next day. So we actually developed then what our plan would be for the next day and set up for that following day as well too. Now we're just into the early stages of analysis, but just to kind of give you all a sense of what we've done in terms of our damage assessment as well as dislocation, this table represents at least the kinds of residential structures we saw in and actually assessed within Lumberton. Most were light wood frame structures with brick veneer. Of average quality in terms of overall construction, and typically these were 1 and 2 stories, for the most part really 1-story structures. About 2/3 had crawl spaces, the rest were slab on grade. Not very good for a flooding situation, but you can see big differences there in terms of the nature of damage as well too. Generally, we're dealing with single 4 structures. Majority, again, were single family residents, a number of multifamily, oftentimes duplexes and triplexes, and then a few larger multifamily structures as well too. These were the damage states in terms of different components of the home as well as the overall damage state. So everything from DS0, no damage, all the way through DS4, although quite frankly the majority of the structures that were assessed were in the range of 1 and 2 with a limited number in 3 and 4 damage states there in Lumberton. Here's an example of 2 sets of fragility curves that for homes with crawl spaces versus those on slabs. So the horizontal axis here represents the flood level at threshold, and then the probability of being in particular damage state. So if you look at, you can see that the probability of being in a higher level of damage state increases, of course, as the flood level increased within those areas. We took that, or we're taking that, and actually then linking that with dislocation data. Overall, about 49% of the households that we, the housing units that we surveyed, and then the households, about 49% dislocated. And you can see there's a direct relationship with damage, right? A DS0, about 25% dislocated, all the way up to 94% at DS3 plus. But also important socio and demographic differences as well too. If we look at tenure, for example, for renters, about 69% dislocation, whereas for homeowners it was only about 48%. And then remember, Judy talked about the ethnic racial breakdowns in the community. We see that there were quite pronounced differentials there as well too. For Anglo households, about 27% dislocated. For African American, 74%, and for Native American, 84% dislocation rates. So very different rates across those spectrums. Taking both of those things into account is critical, okay? This is a map of the community. It's a heat map. The darker the red are where we've got concentrations of higher levels of damage, or higher damage states, if you will. The contour lines represent where we've got concentrations of dislocation. We pointed out 2 areas where damage levels were relatively low, but we see high levels of dislocation for renters as well as low-income households. We're combining those data together to develop probabilities for different kinds of households. And here on the right-hand side, for different damage states, DS0 through DS2 plus, we're looking at the probability of dislocation for renters and homeowners. And you can see for homeowners of much lower probabilities at given damage states of dislocation relative to renters. On the right-hand side, or for race categories here, so the Anglo or white household is the blue line at the bottom, so very low probabilities relative to African American households in red, and Native American households in green. So controlling for damage states, we see very different kinds or very different probabilities of dislocation. So where do we stand, or where are we going? Well, we're combining those together to develop more multivariate models for dislocation, better understanding the phenomena and issues, and a critical one, and that is actually for the first time linking in infrastructure and infrastructure disruption as well too. So we can see clear impacts of those as well too. Looking at dislocation time, and then beginning to analyze initial aid and recovery efforts. Resiliency is all about not just damage, but long-term recovery. And indeed, that's the issue that we are going to be addressing as well, too, of going out and continuing to collect data so we can see those variations in the recovery and indeed the overall recovery process for communities. That's it.
Now we have time for more questions from the audience or those who are joining on the web.
Thank you, Walt. This question's for you, actually. It's 3 parts. How long did the institutional review board process take? Were there any lessons learned out of that you care to share with us? And third, do you think the process may have imposed any constraints that could have resulted in any bias in the data?
Good questions, and I'm actually going to turn it over to Lori and Jen since they spearheaded it through it. But I will say, as one of the participants, were it not for them, we would not have been out there in the field. And part of that was not just simply the Institutional Review Board, but also dealing with the bonehead researchers that were actually involved in the teams and getting them involved as well, too.
So we'll start with how long it took. So we were just looking at each other. This really was a 1 year and 3 month long process from the very first meeting that John and Jen and I had with the Institutional Review Board here at Colorado State University to inform them of the study, and then to begin the process of preparing all of the paperwork, and then beginning to link with all of the field teams and the universities and so forth, because both individual researchers had to go through the training process to become certified, but also we had to have these institutional agreements, and fortunately all of the universities signed on, but it was a big undertaking.
But we worked with, Jen in particular had worked on kind of developing a generic set of instruments that were passed through the review board, so we got that approved, and then it was just tweaking it in terms of our being able to go out. So I cannot say that there was a delay in that sense. There would have been had it not been for them spearheading the effort, but I can't say in terms of that element of delay in time that we saw that.
So and maybe I'll just add as a structural engineer, it was I was really amazed to see the number of documents and the process that unfolded, because before we generally, we just look at buildings or bridges or physical infrastructure that doesn't talk back to us, and so so I was really quite amazed at the amount of effort that goes into that, and then to get this blanket agreement with NIST involved, so just a tremendous effort on Lori and Jen's part.
And I'd like to add to that. I don't know if you paid attention, but in one of Walt's slides where he had all of the team members listed, so this was everyone with a very diverse set of backgrounds, all of us, all the engineers included, right, went through this process. And I think that was really important. I think it felt like a very egalitarian team. And I think having to go through exactly the same process for every single individual that was part of the team was critical in building that atmosphere. So that was really nice. So thank you, ladies.
So in the dislocation models that I've seen before, there's some types of difference between, I guess we would call voluntary versus involuntary dislocation, or maybe short-term and long-term dislocation, however you want to think about it. In your survey instruments or in the work that you did, are you able to distinguish between those two?
Thanks, Charles. That very important, because in our initial algorithms, we clearly saw that in Centerville, And we were able to ask income questions as well as disruption questions to infrastructure. And at least in the preliminary analysis, we certainly see that. We see peaks at lower levels as well as peaks at higher levels with oftentimes much less damage because there are resources available, so getting out of the home for that period of time in which any kind of repair work. So we actually are seeing that as well too. So I'm hoping that we can push that further to actually capture that. Good, thank you.
I'm wondering if somebody from the team can talk about how you, the process of actually being in the field, how you put your field teams together, and what role technology might have played in either assisting the quality or the speed of data collection.
So I'll start, and you can finish up if I don't capture everything. But I think we were very, I don't know if you saw that one picture that had all the writing. We were very good every morning and every evening to talk about where we were at and where we wanted to go. And once we had an objective for the day, then we divided all the team members into multidisciplinary teams so that we always had every single sub-team that went out into the field had a diverse group of individuals within that team. We also did something that was really interesting. We had, that we didn't describe in detail in the presentation, we had an advanced team, which was very important to the whole process. So we developed this, sample protocol. We had a list of housing units that we wanted to study, but we wanted to ensure that what we had was what was actually in the field. And so this advanced team went out ahead of time and asserted that what we were going to look at, or what the teams that followed us were going to look at, were actually there. And that was very critical because it allowed us to kind of change or add new housing units if we didn't find something that was what we were expecting, for example. So I have to say that was critical. The other piece, you asked about technology and assisting us while we were out in the field and with these daily activities. I think that Nathaniel and Walt's work on making all of these housing units accessible on our phones with these Google Maps so that we could see what we were expecting to go out before we went out was very helpful. And then these daily updates, right? So we already looked at all of this. It was representative in the map, and so we knew not to revisit. So it really made the efficiency of our team, I would say it heightened the efficiency of our team, and it made the ability for us to look as many housing units as we did. It would have been impossible, I think, without this technology. So that was helpful.
Yes, and just Yu Zhao actually talked to us. I mean, this was like a week before we went out and said, have you tried Google Maps? And then Don Juan Gu and Nathaniel Rosenheim really then implemented that within the sampling strategy, which was just absolutely amazing. And then to kind of put those housing units in place. Having the advanced team, I think, did help. So we actually spent Sunday and Monday Monday and part of Tuesday going through the areas so we could do that initial screening and make fine adjustments, and so that did really speed it up. It was interesting because we actually anticipated that there would be differences in time for damage assessment versus the household survey. So we had interdisciplinary teams, but we kind of started dividing up, where the engineers would do, and we basically gave up on that because there was, there would be different elements that would just take longer with a damage assessment for a particular structure or a household, and so we ended up just kind of going through the neighborhoods or each of the areas as an integrated team and stuff. So it really worked out great to be able to do that and to do it rapidly. I'm amazed at what we got accomplished. I've been involved in these things before and spent weeks and months collecting data, and this was amazing what we did.
I want to add one more thing, that the evening briefings, which were critical, I mean, they would go on for hours sometimes. I think people were really starting to hate us. But they were critical because you went out into the field and you learned what worked and didn't work, right? Oh, it really, if you want to ask that question, ask it in this way, or if you want to do damage assessments, it's pretty quick to do it this way. And Bill would fill in and say what was working for their team, and it was very helpful because everyone that went out had their own successes and their own failures. And that evening we discussed them and integrated that into the procedures for the next day. And so we were effectively trying to make everyone successful every time and minimizing kind of the learning curve when we were out there. So the morning debriefs were great in organizations, but the evening debriefs were great in kind of tweaking our strategy and our process when we were out there. And that was great.
So you mentioned doing random sampling of physical damage, which engineers typically want to go look at all the damaged buildings and they ignore the ones that aren't damaged. So I would just like to hear a little bit of discussion about how you developed the random sampling and coordinated that with what the social aspects of the study were trying to establish as well.
So I'll give it to Walt, but one thing I want to say is that it was clear in the beginning that the social questions we were trying to ask had to drive the sampling, and then subsequently the engineering assessments would follow, and that was going to be the most successful strategy. But
yeah, that was the nature of the game. So I mean, it was really, we wanted to make sure we got heterogeneity in terms of understanding the various levels of damage, but as well in terms of the different kinds of households and structures that we would see out there, single family, duplexes, triplexes, et cetera. So we defined that space in which we were operating, and then to try to confine things better, doing an initial sampling, proportionate size for the block, census block, and then doing random sampling within those as well too. That two-stage process made it a lot easier for us to get into an area and cover that area rather quickly. It also will give us ultimately great baseline work from the census data as well to move forward in terms of refining some of our dislocation models as well too. I personally, having done these things before and having a bunch of social scientists go, we take the FEMA stuff, we take stuff from NIST and everything, so here's how we're going to assess damage and stuff. It was really neat to have engineers do that part of the thing, but us be involved. We actually, honestly, at some point, we blessed engineers, they became honorary social scientists, and then begrudgingly the engineers blessed us to become, at least for that time period, engineers as well too. So, but I know, it was just temporary. They revoked it afterwards. But I'm quite serious. I think it was a learning experience on both fronts in terms of trying to address those issues. And so now we have good assessments of the nature of damage overall in the community, not just which is important, the unique features, especially for codes and standards of what may have gone on in those areas. So it's really a nice blend of both those approaches.
So we'll take one more question there, and then those that came through email, will respond to them separately.
Okay.
Just one last question.
So now you have introduced the school attendance zone as kind of a new unit of analysis that was not necessarily talked about in previous test beds. So how are you planning to use this to inform some of the work that you're doing in the test beds in the future?
So that's a good question. And I think, if we think about the complexity of community, and the complexity of the nature of organizations, the institutional structures within the communities. And schools are a critical element of that. Critical for households, how schools and children are going to adjust to deal with the issues, and quite frankly, being involved in many of these post-disaster events and everything, getting schools back online can be absolutely critical for retaining population, for normalcy in school. Lori's work on children and disasters is absolutely, fundamental for people to understand what goes on there and how reestablishing those routines can be so important. And so we will combine those together with the data that we collected through the semi-structured interviews with the schools as well too and stuff. So we haven't gotten to that process yet, but we'll have the systematic data. And it was interesting too, because some of the households we could see had not returned, but
there was an impetus to return because 3 weeks the schools are going to be open back up, and the schools, the kids were picked up at the bus stops, and so they were back in the community, back in the neighborhoods and stuff. So it's a really interesting dynamic that we haven't begun to explore, but we hopefully will as well. Thank you.
Okay, well, with that, I'd like to go ahead and close the webinar. And so on behalf of all of the Center of Excellence researchers and collaborators, for those of you out on the internet or on the web, thank you very much for attending, and we look forward to interacting with you at the upcoming conferences and other venues. Thank you.